Hey, Earth Science. As the schedule says, today we're going to talk about stellar evolution, the life cycle of stars from beginning to end. And there's quite a lot to go through. There's a graphic down below that we're going to be following, kind of like a flow chart. I'll be taking notes right over there. My whatever this is will be right over here. So let's get started where the stars get started, and that would be here in the molecular cloud. So we can think of space as obviously being full of all kinds of stuff, but there's just going to be some sort of cloud of gas and of dust. Now, what kind of gas in particular? Most of it is going to be hydrogen. If you look on the periodic table, hydrogen is element number 1, and it is the simplest, lightest, most common element in the universe. Being element number 1, it just consists of a single proton being orbited by a single electron. It tends to form a bond with another hydrogen atom so that you'll end up with a molecule of 2 hydrogens. That's honestly most of the matter in the universe. Now, because it is matter, it means that it's subject to gravity. And so what you're going to end up with is these clouds are eventually going to condense under gravity. When a gas collapses, it undergoes some physical processes. Now, as you can see, molecular cloud, there's a green arrow that leads down to this little spot here, protostars. So let's get to that. So there is a formula that you learn in chemistry or physics, whichever you take first, about gases and their properties. And actually it looks like this. Pressure and volume are going to be proportional to, well, I'll just put a couple numbers here. You don't have to worry about N and R. This is pressure, this is volume, and this is temperature. And not to get too deep into the weeds of the chemistry here, but if a cloud is collapsing, it means that the volume is going down. Now, because this is out in space, it means that heat is free to come and go. So the temperature is able to stay the same, but the pressure is not, because if this side stays the same, then in order for the math to work out, this pressure is going to have to go up tremendously. Now, like I said, not to confuse the issue with too much chemistry, the point is that when this cloud is collapsing, what's going to end up happening is all of those hydrogen atoms are going to get really tightly crammed together. And when atoms get really tightly crammed together, they start to produce heat. And so that's what we end up with in these protostars, okay? So we're going to end up with very dense collections of hydrogen. I'm writing H2 as an abbreviation for hydrogen, that are at increasingly higher temperature, higher pressure, and because the mass of so much hydrogen is in one place and gravity is a property or is related to mass, the more mass you have in one place, the more gravitational attraction you have in that one place. And that just means that you've got even more gravity this is going to run away, and eventually it's going to cross a threshold. And what's going to happen is there's going to be the beginning of fusion. Now, I want to take a moment to talk about what fusion is, and then we can follow the next path into an actual star's life, because right now we're knocking things over. Right now we're still in the protostar stage, and if I can just get a new sheet here, want to understand what fusion is. Now, when you're studying, science in school, there's a couple different sciences. We got physics and chemistry and biology. We are usually studying the behavior of atoms in chemistry. And basically, everything that happens in chemistry is like this. There is a nucleus and some electrons. Then there is another nucleus and some electrons. Basically, everything that you learn in chemistry is somehow the behavior of these electrons. Most of what you think of as stuff with atoms is just electron business. This is where we cross that line. So we are going to have, and now I'm going to use some colors to help you keep some things straight. We are going to have protons and electrons. These are atoms, hydrogen atoms. Okay, so the positively charged proton in the center, the negatively charged electron around it. If these two were to link up and kind of become like a figure 8 or a dumbbell, you'd have a hydrogen molecule. That's chemistry. But the pressure that is going on in the center of these protostars is higher than that. If you get enough mass in one place to create this kind of pressure, what's going to happen is these two are going to be pushed together, not just so that the electrons overlap, but so that the protons actually end up overlapping, and you end up with a badly wrinkled piece of paper, or you end up with both of these protons at the center of a new atom. Okay, so we've got proton number 1 and proton number 2. They are now both inside of this new atom. We have electron A and electron B, and I have both of those electrons in this one atom. Because this process involved the nucleus, the nuclei of these atoms, this is not a chemical process. It is a nuclear process. Now, if we had split this atom into those two, it would be called fission. And that is the nuclear process that powers nuclear power plants and is the explosive force behind nuclear bombs. This one, going from two atoms into one, is the opposite. That is called nuclear fusion. Now, I've drawn this super duper simply. There's a lot that's missing from it. So rather than bug you with all of those details, I'm just going to leave it as simple as this. If you want to know precisely where the energy comes from, I would also need to include neutrons. which undergo part of this process. That's the kind of thing that I can just put a link for you to check out if you're curious. But the big picture is you take two atoms and you force them together to form one new atom. A lot of energy is released that raises the temperature, that raises the pressure, and it just gets a whole lot worse being in that neighborhood because the atoms are detonating around it. So at this point, we finally have a star. And if I could draw a very, very generic outline for a star, what you're going to have is a core at the center where the pressure is the highest and the fusion happens there. The fusion is happening in the core. And there is obviously superheated gases and plasma around that, but the fusion itself is happening in the core. And basically, the way that this star's life will progress depends on one thing, mostly, which is related to several others, and that would be the mass. And the reason why it's, kind of like is it one thing or is it several things, is because the mass itself is going to determine a lot of other things about the star, but they're all related to each other. So it's kind of like one factor that shows up in several places. So how much mass is also going to determine how bright the star is. It's also going to determine how hot the star is. That's also going to determine what color the star is. And obviously how big. So these things are all closely related, and I can start by going through this chart down there, and we can actually track the life cycle of some stars according to their masses. So let's head down the lightest ones. And as you can see, this is called a brown dwarf, and the mass is less than 8% of the sun. So we can consider, I don't even have a brown marker. That's too bad. So we can consider a brown dwarf as, hey, good game, we tried, but we didn't really end up with a star. A brown dwarf is so close to being a star, but it never got enough mass to produce enough gravity, to produce enough pressure to cause the ignition of fusion. Brown dwarf is almost just like a really hot planet, hardly even a star. So if you think about like Jupiter as a really, really big gaseous planet, if you had, maybe 10 Jupiters, the pressure at the center would be enormous. The temperature would be really, really high, but it wouldn't be enough to trigger fusion. And so you'd end up with a brown dwarf. So that's really just the end of it. I think as rude as it would be, I don't mind calling a brown dwarf a failed star. I don't think that marker wrote very bold, did it? Looks like my failed star is actually a failed marker. Failed star. Anyway, so that's what a brown dwarf is. So, wah, 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 wah. Anyway, if we get above brown dwarf, we're finally to the point where we could end up with a star. And if we stay within 8 solar masses, so you see this says less than 8M sun, that means we are between 8% of a sun, and 8 suns. So our sun is, in this range of what would be called a low mass star. And so let's see, I'll go orange on this one. So a low mass star. Okay, that's going to be a mass that is less than 8 suns, but greater than 0.08. Didn't give myself enough room. Suns. Okay, so what about this low mass star? This is going to kind of repeat for the high mass star. It's just going to do it differently. So depending on the actual mass, the life of the star could last anywhere from trillions of years to hundreds of millions of years. But it depends on its mass. So if you had a mass that was like, say, 1 sun, it would live approximately 10 billion years. That's a B. If it had a mass of, say, 3 suns, we're talking about like 370 million years. Our sun right now is about 4.5 billion years old, which means we have a middle-aged sun. We're expecting it to live 10 billion years. It's currently almost 5. So you're looking good, sun, halfway through your life, and you couldn't be better. Okay, so what is the actual course of this? So as you can see, the next step is a red giant. So let's talk about how a star, a low mass star, becomes a red giant. So you had in the last slide that it has a core in which it does its fusion. So let's redraw that. We've got a sphere that is pretty much all hydrogen. And the hydrogen in the center is fusing. Well, what's the product of that fusion? 2 hydrogen atoms fusing turn into a helium atom. Now, helium is atomic number 2. There's 2 protons, 1 proton from each of these hydrogens. Okay, so that means that the core of this star is becoming less and less hydrogen and more helium. As that happens, the helium is harder to fuse than the hydrogen is. So as the usability of the hydrogen decreases, what happens is the core compresses and becomes more dense, where this outer shell expands, becomes less dense. So you end up with something like this. I think I've got room to sketch this. Can't really make it bigger, so you just have to imagine that this is bigger, sorry. So a core that is compressed, and then an expanding outer layer. So red is cooling. How does that work? Well, let me get my colors out. So colors of the rainbow being red, orange. This is the only yellow I have. Sorry, it doesn't match. I'm sure that really offends you. Green, more green. All right, so as I get these colors out, you will recognize them as being in the order of the rainbow. And if you remember from the false color image, This is also in order of wavelength or frequency. Now, according to the physics, what that means is they're also in order of energy, which means red light has less energy in it than blue light does. Yellow light has less energy in it than green does. So if you have a star that is broadcasting all energy, even if it peaks a bit in the middle, basically all these colors mix, you end up with, like a prism in reverse, it all mixes to be white. So what happens if the star cools down? It's going to send out less high energy. The high energy is going to drop off the most. All right, so at this point, with the violet and the blue being gone, most of what's left is in the greenish and reddish. That's yellow. If you have a green pixel and a red pixel, they illuminate to make yellow. So let's have it cool down some more. Purple and blue are completely gone. Now the green is starting to go. Well, look what we have now. Mostly yellow, orange, and red with barely any green. This just went from white to yellow to orange. Cool it down some more. Green is gone. Yellow is diminishing. We barely have any orange. Basically, all that's left is red. So this is why it will be red as it cools down. In fact, if it were to cool down even more, to the point where not even red is shining, the only color left would have been the invisible ones that were to the left, infrared. Everything is glowing infrared. It's just, it needs to get up to hundreds of degrees before it starts to glow red. Stars are like that. So a red giant refers to a star that is cooled down enough to not be white anymore, but is now red. When our sun becomes a red giant in billions of years, it will become so large, it will envelop the Earth's orbit. That's how big that is. But the core will still be quite small, and it's going to be mostly helium. So we've got a couple options after this, and I want to explore them both. So this red giant could become binary with a white dwarf, or it could become a planetary nebula, which leads to a white dwarf. Let's take this path because it's the bigger arrow. It's the planar one because it's the one that doesn't involve an interaction with another star. So let's go planetary nebula. As you can see, planetary nebula is a nebula, and it kind of looks like a ring. That would basically be this core fizzling out, so to speak, and all this expanded gas just kind of like escaping. And that is called a planetary nebula, and that would be kind of like a ring or a halo around the star that might eventually form something else. What about the white dwarf? Well, the white dwarf at the end there is just the leftover core of this star. So a white dwarf is still hot, glowing white, because it has enough pressure to continue fusing its helium, to not have cooled down yet. But its life is essentially over, and it's just going to spend the rest of its years cooling down until it becomes a black dwarf, which is just a dead star. Let's take this more interesting path, though. A red giant may end up binary with a white dwarf. Now, as you can see, there's this trail leading off here. So because this star is so massive, it means that this gas here could be, dozens of millions of miles away from the core, which means a compact mass nearby to it may have enough gravity to kind of, steal some gas that's going to kind of, wisp and peel off of this red giant and start to collect on this. Well, there's two different options for this, and it, again, has to do with the masses. If the mass is less than 1.4 masses of the sun, you get a nova. And if it's greater than 1.4 times the mass of the sun, you end up with what's called a type 1a supernova. A type 1a supernova is one of the standard candles that's used in calculating stellar distances from the last video. But let's just talk about the word nova for a second. The word nova is etymologically related to the word novel. The word novel as in like new or unusual. Also, sorry, I don't know Spanish, but it's related to the word in French, nouvelle. It's the same root. And just in case you know this one as well, it's also related to the word for Christmas, Noel. Those are all related to each other, and they all have to do with new, as in, the good news of Christmas, or this word, which literally means new, or novel, meaning different or unusual, new. The word nova means new because when a nova was first observed hundreds of years ago, it was a spot in the sky that was dark that then became light. And the observers who saw it thought it was a new star. So they called it a new, nova. Turns out it was actually the end of a star, not the beginning of one, but that is where the name comes from. So basically, it's a big boom or a little boom. What's the boom? Well, as all this material collects around this, you get a sudden, again, collection of material, and a sudden collection of material is what causes a sudden spike in pressure, which reignites fusion and sends the material out, and there's your nova. The white dwarf would again be the leftover remnants of that nova, which turns into a black dwarf at the end. Type 1a supernova is the end because there's nothing left. It's just the nebula. So there are some nebula in the sky today which just are the results of supernova. Think of it as the, the explosion, you might say, is over, but it's just like the remnants still expanding. Anyway, we did a brown dwarf, a super low mass star. Then we did a regular low mass star. Maybe we should have said that was like medium or something. Okay, this is almost like, some sort of weird fast food soft drink sizes where there's no small. It just goes straight to medium. Anyway, we have massive stars, which are greater than 8 times the mass of the sun. You'll notice it's a different color. Here's why. When it comes to high mass stars, let's see, let me get this here. Massive stars. Oh, I should have done it in blue. I guess I'll just do this in blue. Missed opportunities, Hold on, my camera's gone out of focus. So when it comes to massive stars, I'm just going to have to wait for it to get over itself. When it comes to massive stars, we're talking about ones that are, there we are, greater than, the mass is greater than 8 suns. There is, there we go. There's so much mass, meaning so much gravity, that the intensity of the pressure in the core is higher, which means more gravity means more fusion, which means more energy, which means higher temperature, and more fusion also means shorter life. You know those battery commercials, extra power or more life? Turns out that extra power is less life in the case of stars. So if we're talking shorter life, I'm talking about like if the mass were 10 solar masses, it's only expected to live 32 million years. 10 suns, we're only talking like 32 million years. If it's got a mass of 30 solar masses, 30 suns, we're just talking about 11 million years. That's like, okay, never mind. I'm thinking of the next one. 60 suns. Now we're talking 3 million years. That's not much longer than the time span in which humans have lived. So when it comes to like low mass stars, we're talking about they have lives as long as our planet's entire history. But very, very massive stars can have lives as short as the human race. So yeah, that's quite a difference. Okay, so you'll also notice that it's blue. Okay, why is that? Let me get my rainbow back out here. Roy G. Never thought that would help so much in life, but like just knowing the order of the colors in the rainbow, it's kind of a big deal. You don't want to get caught not knowing that. Okay, so there's the colors. The idea is really high intensity means the average energy is higher, which means this side is bumped up and this side is down. So if all these colors were even, it would be white, but since it's leaning on the blue side, the stars will appear blue. Most of the energy coming from those stars is in the higher range, and that makes them blue. Okay, well, when it comes to these massive stars, because they are so dense, the distinction between the layers, like having a core and the non-core, is not quite so even, because you have a core, right? But then you have layers of decreasing density where the core is not the only place dense enough to cause fusion. And so what you're going to end up with is these stars are producing fusion and therefore new elements in various gobstopper-like levels, so that I think I might be overdoing it with these rings. There are lots of levels of atomic fusion where different elements are being made. Now, just like in the last one, the usable fuel is going to be used up, and that means that the fusion slows down and the outermost part is going to expand. This is where it gets nasty, because there is actually a limit to which fusion can occur within a star. So if you were to look on a periodic table, you can see that there is an order to the elements that they'll fuse into. And so we got hydrogen, which is element number 1, helium, which is element number 2, element number 3, element number, hold on a second, 4, element number 5, element number 6, element number 7, and so on. I'm really doubting myself on this one. I don't know. I just haven't looked at a periodic table in a while. And you could keep going with this, just like it was math problems, like a helium plus a lithium equals a boron, right? Or like two lithiums make a carbon. Like you just add atoms like that. You get to a point though where actually the temperature and pressure of a star, even a massive one, is not sufficient to add past a certain number, and that number belongs to iron. Turns out that iron is the element past which a star cannot fuse. So what's going to happen is iron is going to start to collect in this core. As the star expands into a red supergiant, right? The fusion slows down, the star cools and expands just like before. But here's where the difference is. Once the star, when the lighter star ran out of hydrogen, it was running on helium. When this star runs out of usable fuel, it really runs out of usable fuel. And it's just stuck with iron that it can't go past. The fusion shuts off, and then the star collapses because the only thing keeping it out in the first place was all of the energy being released by fusion. But as soon as that fusion shuts off, this whole thing just collapses in a second. Okay, we're talking about several, even a dozen solar masses collapsing in a very small location almost instantly. The pressure buildup from that is enormous. One of the highest one of the highest pressure, highest intensity, most violent occurrences in all of the universe is the collapse of this red supergiant, and that is why that leads to a type 2 supernova. A type 2 supernova is, because that's, anyway, a type 2 supernova is the death explosion of a supermassive star. And because the intensity of that collapse is so much more than the normal intensity of the star during its life in fusion, that means that a type 2 supernova, brief as it is capable of performing fusion past iron, which means any element past iron, like silver, gold, copper, mercury, all of those past iron in the periodic table were not made in stars. They were made in the deaths of stars. A type 2 supernova is so furiously energetic. It is the brightest thing in its galaxy at the time. And there are a couple different paths for it to go. If it is less than 40 times the mass of the sun, the remnant is called a neutron star. Now you remember the remnant of the smaller explosion, the nova, was a white dwarf. A neutron star is, you might think of it like a white dwarf, and it's still very hot. It's just that it's all neutrons. There's no protons left in it. And it's also spinning very, very quickly, which is what can cause it to become what's called a pulsar. So this is a thing which we would have been able to do in our classroom if we were there. But maybe you have a chair like this. But this is something that you guys did. Particularly, let's see, who would always sit in my chair? Uriel, you'd always sit in my chair, and so I think Mitchell also sometimes. Tobias. Anyway, no one sits in that chair now. Anyway, so when you're in a chair and you're spinning, I would spin right now, but No, I just hurt myself and it'd be recorded and that would be embarrassing. So as you're spinning, you know, if you bring your arms in, you speed up. And when you put your arms out, you slow down. Well, stars do rotate. And just like when you bring your arms in and you speed up, when a star collapses, it becomes more, you know, like arms in, so to speak. It speeds up too, which means neutron stars can spin very, very quickly. One of the things that comes out of physics is that spinning electrical charges can produce magnetic fields, which means that the magnetic field of a neutron star can be like one of the strongest in the whole universe. And a pulsar is when there are jets of X-rays that are kind of being funneled out the poles of a pulsar by its magnetic field. And, you know, kind of like I'm picturing like a water balloon that has a leak in it spinning in slow motion, just kind of like squirting water out in all these different directions. As this pulsar rotates, if you happen to be along its pole as it rotates, you're going to get like a little boop of X-rays. So if you're observing in the sky with an X-ray telescope and you just get like a pulsing X-ray in one spot in the sky, you're probably looking at a pulsar. In other words, a magnetic field, super duper uber strong, from a fast rotating neutron star that's funneling X-rays in your direction, that is the result of the collapse of a massive star. Okay, so that's if it's less than 40 times the mass of the sun. What if it's more? Oh, you know what? Hold on. I should write that down because this is the good stuff. That's right. This is the good stuff. So if what was it? So if a star, this is a massive star, collapses to make a supernova, if the mass is less than 40 suns, we end up with a neutron star. And if it is greater than 40, we have a black hole. Oh, I missed a little branch there. Supernova remnant. That would be kind of like the Planetary Nebula back from a red giant, except it's you know, from a bigger star. So if that supernova was greater than 40 suns, we have ourselves a black hole. So what is a black hole? A neutron star is a super dense, very, very dense collection of matter, as dense as matter can get and still take up space. A black hole would be from a collapse so strong that the laws of physics for the normal universe do not permit that much mass to be in as little space as you get. This black hole contains within it something called a singularity. And a singularity is essentially a volume of zero, which is, well, here, if density is equal to mass divided by volume, if you have a volume of zero, you're like dividing by zero. So this is why I say the normal rules of physics don't permit this. Now, when I say normal rules of physics don't permit something that's real, obviously what that means is the normal laws of physics are actually incorrect. The things that we understood about physics in the 1700s that we got from Isaac Newton were awesome, but they weren't everything. And we needed to learn some more things about gravity and about space in the early 1900s. That's what Albert Einstein did with relativity. And so there is some pretty crazy, awesome, possibly even evil math that I never even learned in college, but that I know about, that makes sense of black holes in a way that the way that high school physics doesn't. So if you're curious about that, that would be a great topic for, later. But just for right now, if the mass is less than 40 suns, it will collapse and be super dense. If the mass is greater than 40 suns, it will become, let's just say, impossibly dense. And you end up with a black hole. We finally got a picture of a black hole. It was M87. I'm sorry, it was in galaxy M87. And that it was like that fuzzy orange ring. Maybe you saw that last year. And just kind of like you've got a pulsar from a neutron star, you get something similar from a black hole. And if you get a black hole, then you get a movie like Interstellar. Anyway, we went through the life cycle of stars, whether they be very light and not even really a star, low mass, such as our star, and that would be between 0.08 and 8 solar masses, and then a supermassive star. They have a similar path in that, let me zoom out here. They have a similar path. In a second, I just messed up my winders. Yes, that's right. I said that. They have. Oh man. Here we go. We have a similar path in that they both end up as giants, and then they both collapse. The difference is that this collapse is so extreme that it kills the star, and you end up with either a hole in space or in a like super dense dead core, or it's not so heavy and it either just sheds some gas and its core cools off till it's dark, or it gets into a tangled mess with another star, which causes a littler explosion. Anyway, this all this stuff here is things that we've only known about in the last century. This is actually kind of new science. When I say new, I mean like relatively speaking. This is still an area of active research, but all of the stuff that is on this chart is well established. Stuff that we don't know would be stuff like what's it like going into a black hole, stuff like that. Things like, yeah, it's usually this stuff that we don't know about, the dark stuff, because the bright stuff is easy to see. All right, well, I think that I've made this long enough. I could add to it, but then it'd be less fun because it would be too long. So I'm going to stop right there, and I will see you on the next one.